Already, we showed that the rule amounts to a relabeling of the p states. We have 6 p states. We have 2 ways of labeling them. You can extend it to d states, f states, and at the end, you will have just no more and no less electronic states. Today, the first thing I would like to do is to extend this addition of an orbital angular momentum to the spin angular momentum to the case of adding 2 spin angular momenta. That will be useful first, for example, in helium atom, we will have 2 electrons, each spin half. We will have to think about how to add them into a total spin angular momentum for the helium atom's 2 electrons. And more importantly, when we think about how to add them, that should be the a first way in quantum mechanics to get a sense of what is entangled states. We will find that the rule of adding 2 spin will give us an example of having a state where these 2 spins will be forming a state that if you know the spin of one electron, the other one will be fixed as well. That is a standard situation in something called entangled state. We will have the first encounter by thinking about adding 2 spin. The next very important topic we will discuss today in some detail is the spin-orbit interaction. The first thing I would like to do is to introduce the form of the spin-orbit interaction energy, because that will appear in the Hamiltonian. The second point that why we want to discuss it in our course is that suddenly in condensed matter in the past 10 years, this spin-orbit interaction effect becomes very important and very popular. It is very important among a class of materials. For example, nowadays you may have heard something called topological materials, a very hot topic in condensed matter physics, no matter in theory or in experiments. All of a sudden, the scientists found that there is a way that you don't need to buy a big magnet, and yet you will get a magnetic field. And electrons in a magnetic field is a very fascinating topic to understand, to investigate, and make use of. So it is because of this reason we will spend some time in at least understanding the physical content of spin-orbit interaction. With that, we have the perturbation term, and we can use perturbation theory to investigate how the spin-orbit interaction term will change the hydrogen's energy eigenstates. So that is the plan. We will see how far we can go. So let me quickly remind you of the rule of adding an L orbital angular momentum to a S. Last time we proved, rather long proof, that this is well, adding 2 angular momenta is an angular momentum is very natural, and because it is an angular momentum, it obeys all the general rules that follows from the commutation relations. We proved it last time, so we can make use of it. So at the end, the whole problem becomes, if the orbital angular momentum has a quantum number small l, and spin is spin half, s is half, what could J be? So this quantum number corresponding to the total angular momentum. I give you the rule. For an electron, it is always half for the S, and L could be 0, 1, 2, 3, representing S, P, D states, or etc., higher states. And the rule becomes the J can take on L plus half and L minus half, as long as this resultant J is positive. It cannot be negative by definition. I mean, from the commutation relations. So there's only one case that we should be careful for S state, L equals 0. This will be found out because that will be J equals negative half. That is not possible for angular momentum's length magnitude. Therefore, if it is an S state, only take the first rule, okay? And we demonstrated that is nothing more than relabeling the states for the example of P states. So for P states, we have 6 states in the ordinary labeling, meaning orbital angular momentum, L, M, L. We have 3 numbers, 1, 0, minus 1. And then you use S, MS. MS is spin up, down, plus half, minus half. 3 possibility multiply into 2 possibility gives you 6 combinations. This is the 6 P states. Along the periodic table, you have some elements, but that is the next topic that we will discuss, how to handle multi-electron atoms. Okay, that is something rather highly non-trivial, I would say. And then in our new labeling, we don't use ML, MS. We already add up the L and S to form J. And underneath J, there is an MJ that goes from plus J to minus J, referring to the Z component. So following the rule, for P state, J will have 3 half and half. And behind this 3 half, there are 4 states. Behind this 2 half, we have 2 states. Altogether, 6 states, no more, no less. That's why I'm saying that it is it amounts to relabeling the 6 P states. For the more mathematically inclined student, this relabeling is actually carried out by linear combining these 6 states and resulting in 6 linear combinations. And they will be labeled differently by J and J. So one can use a baby level of so-called vector model to think about it. But again, it is only a picture to carry with. You shouldn't take it very seriously. So for the longer projection, the largest projection being 3/2, you can think about it, this L and S are more or less aligned in the same direction, meaning they are by large pointing towards, say, up, okay? So the resultant J will be longer, and thereby a longer vector will have more Z, and longer and more Z components. That is the 3 half case. And then the J equals half case, you can think about it, L is pointing largely up, and then S half is pointing down, okay? So remember, for spin half, you have 2 cones, one going in the upper portion, the other one in the lower portion. So this J equals half 1, you can take it as in the lower cone. So it is here, okay? And then that will give you a shorter J, whereby you will have a shorter Z component and only 2 values. Then the first reminder or warning flag is that we know how to add angular momentum in quantum mechanics because they remain in the same family of quantity, still angular momentum, and we know the properties, okay? So in quantum mechanics, the rules are derived for adding angular momentum. But remember the physics is that orbital angular momentum is accompanied by a orbital magnetic dipole moment, and spin angular momentum also has its spin magnetic dipole moment. An analogous question is, how about the total magnetic dipole moment? That's easy, we just add the two, okay? But there is one trouble that will emerge. Remember, there's a G equals 2 factor for spin and G equals 1 for the G factor for orbital angular momentum. So this mu L is related to L by this factor. If I multiply h bar divided by h bar, you will see the Bohr magneton. And then the mu S is related to S with this ratio, but there is a difference of a factor 2, okay? And actually, there's a G factor here being 2, okay? Therefore, if we pull this common factor out, okay, we do not get L plus S. Instead, we have a very funny thing called L plus 2S. You can think about this as the G factor, all right? So, and L plus 2S is not J, because J is L plus S. Conclusion, we know how to add the angular momenta. Fine, we get J. But formally, the J will not follow in the same form that will give us a total magnetic dipole moment. We have L plus S because there's 2S, okay? So that will cause us more work slightly later when we need to handle spin orbit interaction and the effect of a magnetic field, things like that, okay? So at this point, just be careful, okay? Formally, the total magnetic dipole moment does not go with J, okay? Later on, of course, we liked this relationship or this form very much. We are going to find some way to approximate this form out, okay? And how? That is the interesting point to discuss later on, okay? So this is just a warning sign. And now, I would like to discuss how to add two spins. We can generalize this rule, both, after all, spin 1, spin 2 of 2 electrons, they are indeed angular momenta. So they follow the same rule. That's the point. So we would like to see how to add two spin half stuffs. You may think of the two spin half electrons, okay? And then they live in the helium atom. So we need to find a way to find the total spin angular momentum of the helium atom. So that is the context, the first context. Actually, in any other atoms, you have 15 electrons, you have 21 electrons, then you have to find ways to add them anyway, okay? But if we know how to add two, then after adding two, you add this resultant to the third one, you know how to add 3 spin half stuff and so on. So the key thing is how to add 2 spin half. Well, follow the rule. We just pretend one of the spins to be the orbital angular momentum, just angular momentum. So we just follow the rule, right? There are two possibilities, L plus half, L minus half, as long as it's not negative. So now instead of the L, we have another half, because that is the fixed quantum number, Okay, so we have half for electron 1, for example, spin number 1, and another one also half. So we follow the rule. L plus half now becomes half plus half, so it's 1. L minus half now becomes half minus half, which is 0. It's still okay, it's not negative. So, summary, the two possibilities for the total angular momentum quantum number characterized by S will be 1 and 0. Okay? And then recall what this means. It means a resultant of this length. This is length square, okay? This is the alpha, okay? So this is length square, S times S plus 1 H bar square. So two shorter one can add to a longer resultant of this magnitude square. And since S is 1, this will have 3 Z components, 1, 0, minus 1. Okay, so that will account for 3 states. The other possibility has S equals 0, basically meaning the two spin half vector cancel. Okay, so one go in this cone, one go in that cone. However, they always point in the opposite way in this vector model idea, they cancel. So S is 0, no length, and therefore the Z component can only have one thing, nothing, so 0. Okay, so this is another state, but one state. So all in together, there will be four spin states here. Okay, into S equals 1, accounting for 3 states, and the other one accounting for 1 state. Okay, get me? Now, in the previous case, I've been emphasizing is relabeling the total number of states. Think about it. We have 2 spin half. You can think about it as spin half means either Z component is up or down. Now you have 2 of them. Therefore, indeed, you have 4 possibilities, right? Up, 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 down, down, up, down, down. Okay, so naturally you have 4 states. And now, by adding them up to treat the total, we also have 4 states. No more, no less. Same story. Okay, get me? So this is what I just said. Okay, if you think about it in the old label, meaning haven't added them up yet, it is MS number 1 spin, MS number 2 spin. The S1 and S2 are boring half always. Okay, usually we are so lazy that we will not mention this half again because it's always half, and then we have half, half, half minus half, and so on, or even so lazy that we represent by an arrow. Okay, all in all, we have 4 possibilities for 2 spins. Okay, and now if we label it by the total S, we have 1, 0, and then under 1 we have 3 values. Under 0 we have another 1 value, and altogether 4 states. No more, no less. Okay. At this point, it is useful to take in 2 names because this turns out to be very important in modern quantum mechanical problems. The S equals 1, since it carries 3 MS values representing 3 spin 1 states, this particular set, S equal 1 case, is called the triplet states, meaning 3 states behind it. Okay, similarly, the S equal 0 situation will be called singlet states. This labeling will be used widely in atomic physics, in molecular physics, and in many modern quantum mechanical applications. For example, some group in our department like to use some nano diamonds with some defects in it and to measure a tiny magnetic field, things like that. They also make use of this triplet singlet state of the defect. Okay, because a defect is, for example, missing an electron, meaning you take an electron out, therefore there is a missing spin. You can also label the defect in this way. So that is the mathematical conclusion. Okay, this is formal. To help you think, again, this is a classical representation or an artistic way to represent the result, just to help us remember things. This is the vector model. It's a model, okay? So how can we think about this triplet singlet state? It's easy to think about the singlet first. So you have a spin half plus a spin half stuff, and they always cancel so that you get nothing at the end, okay? So you can think about it as the following. One spin lives in the upper cone, so the Z projection is always plus, so it's an up. And then the other spin always lives in the lower cone, the Z component is always down, it's negative. And they so coordinate themselves that this direction is always the opposite of the lower cone direction. So all the time they point in the opposite direction, they cancel each other. Okay, so it's something like this. Okay, so this live in the upper cone. This live in the lower cone, okay? So they are spin half entity. Now they add them, they somehow coordinate themselves like this, okay? And they continue to move like that in the vector model, okay? So that the Z component always cancel fine, and also the magnitude becomes 0. That is the picture, okay? I emphasize again, it is a classical artistic way to represent the result. And similarly, for the S equals 1 case, it's easier to think about the MS equal 1 and MS equal -1 case. You can think about it, they both live in the upper cone, okay? And then they tend to add up. So you have an S and another S, it adds up to a longer one, so that the Z component will be longer, okay? It becomes 1 H bar, right? So half H bar add into the half H bar projection, give you the longer projection. Similarly, for the S is -1 case. The middle case, MS is 0, needs some attention. It is 0, MS, and then this also MS is 0, okay? But this case, as we just point out, they are in opposite direction, so that the vector actually cancels, okay? So there's nothing there. However, in this case, the resultant vector has a length. Now, only that, you can think about it as they coordinate themselves like this. So as they rotate, but they coordinate themselves like that, okay? So that the Z component cancels, however, there is an X component that is rotating around just as long, okay? And that is the vector model for any angular momentum, right? So for any angular momentum, you have this, you have that, you have this, you have that, and so on, okay? Depending on what is the quantum number, okay? For example, L equals 2, you have 5 these cones. One is flat on the XY plane. Okay, so this is how we depict, or it is very popular about among the experimentalists. Okay, they do the commutation relation quite abstract, but this is the picture to carry around so that they can think about how to develop this physics into applications, for example. And spin is very important because it is related to magnetic materials. We have magnetic materials because those materials have net magnetic dipole moment due to electron spins. Okay. Not due to orbital, usually. It's the spin that matters. That's why spin is important. So now we know how to add them by the rule, and we have some picture. The last thing I would like to point out is that where will it be useful? Okay. Later on, we will discuss the helium atom. For example, helium atom in ground state. Well, I think all of you know at least from high school or from year 1 chemistry, although you probably don't know what it is talking about. We have some ground state called 1s for the helium atom, in which we put 2 electrons. And we ought to put it one up and one down, and you found out this case, right? Pauli said no, right? And therefore, if this were the case, it will be S equals 1, 2 ups, longer resultant, okay? But Pauli said, oh, this is not the case. You shouldn't have S equals 1 here. Therefore, the ground state will be S equals 0. We call it helium ground state is a spin singlet situation. We will have more to say about the actual form. Then it is very interesting if we extend the discussion to excited state of helium. We have 2 electrons, so again you can think something like a hydrogen but with 2 electrons. So you have 1s, the next higher level will be 2s, nearby there will be 2p, okay? So now you have 2 electrons, then you start to think, how can I put these electrons, one in 1s, another in 2s? And suddenly, you really have the choice. You have this up, up, or down, down, rather naturally, or down, up, up, down. They're all legal now. Pauli said yes, okay? Could be. Therefore, you really have the choice whether the spin singlet state or the triplet state will correspond to the helium first excited state, meaning which situation will have lower energy. All right? So later on, we will look into this problem. At that time, we will have the 1s, 2s wave function of the helium atom, and then we will see whether the spin triplet situation or the spin singlet situation will correspond to lower energy. Why is this so important, this problem? If we know the answer, let's say, that is true, and not let's say. In helium, excited state, it turns out this triplet state has slightly lower energy. And that is the first time in the history of science, I think, that we started to have some understanding about why the spin of 2 electrons would like to align, to tend to align. Remember, spin triplet means by and large, the 2 spin are aligned, right? You said component add up to longer. Either in that direction or that direction. The resultant is longer, so they tend to add up, okay? We will look into why in helium atom it's all Coulombic interaction, right? Electron sees the nucleus, electrons sees themselves. All Coulombic, nothing new, all Coulombic. Nonetheless, with the spin possibility, there will be a difference between spin singlet energy and spin triplet energy, okay? And it is due to this effect. The name is called the exchange effect. Or exchange interaction, that we now understand why we have magnetic materials, okay? So magnetism has been around for thousands of years, the phenomena. Only 100 years ago, through quantum mechanics, we started to understand why there are magnetic materials. It's quite profound, I think, in humanity, in the history of humankind. And more, when we learn more about how to write the combination, right? So we know that there are two ms equals 0 state. And this obviously correspond to ms equals +1, both up, the Z component add together longer. And this obviously ms is -1, so no problem. These two will be the S equals 1 members. But S equals 1 has a third member. We use these two situations. What remains to us is these two situations, up, down, and down, up. It turns out that, and we can prove it by operator algebra, that we use these two situations and make two linear combinations. Up, down, plus down, up, and up, down, minus down, up. And this two corresponds to both being ms equals 0. However, one has a longer magnitude, one has 0 magnitude. And these two spin linear combinations is very profound in terms of modern efforts in quantum mechanics. They are examples of entangled states. The characteristic is that it is a combination of both possibilities. So if you were this first particle, by quantum mechanics, you are both in up and down state in this combination. So is the other guy, okay? So if you are born this way, your fate is coupled with the second spin. So there are experiments nowadays, well, actually maybe 15 years ago, 20 years ago. So at birth, there are two particles, and they are in such a state. And physically, they fly apart before any measurement is done. So there is a distance between them. But they are still in such a state. And now, if some measurement is done on this spin, this particle, and it was found is up, okay? Let's say this is the first one. So suddenly, by measurement, the state collapsed to this part. Therefore, you don't need to worry about what happened here. This part must be down, okay? But it is only until you make a measurement on this one, and then that determines at the same time, simultaneously, what happened to this particle. The first thing, I think the first experiments were usually done using photons, not matter particles. Okay, photons, there are polarization this way, the other way, it's entangled. Okay, and that is one important part of what is called the second quantum revolution that is going on now. The first quantum revolution refers to what happened since 1930s. So we understand metal, insulators, semiconductors, and then we have semiconductor industry. We have what you have in the phone now. Okay, they are all about behavior of electrons and its charge mostly. But in recent years, all countries, major countries around the world invest heavily into what we now call the second quantum revolution. And the goal is to explore the applications of two quantum elements, superposition and entanglement. So these two things are very important, for example, in quantum computing. You can do parallel computing, many parallel computing at once, right? Okay, and entanglement, for example, is very important in cryptography. So those are very real and recent developments. Okay, so that actually, if you think about it, is it very fancy? I would say no. It is just helium spin states. So I would stop this discussion on adding two spin up to this point. But this page is meant to point to the higher level topics for some of you who want to learn a little bit more. Okay, then the first thing is that it is closely related to magnetism. And there is a field coming up in applications called spintronics. That is to go with electronics. Electronics means we use electrons charge, Q or minus E, okay? So all the applications about semiconductors, for example, are using the charge properties. Electron minus E charge, something funny thing called hole plus E charge, things like that. It's still charge based. But since 1922, Stern-Gerlach experiment, we know electron has spin. However, the spin properties of electrons have not been fully exploited and applied. We have some, for example, the read head, the hard disk, those things make very good use of the spin of electrons. Nonetheless, will there be something analogous to electrons where charge moves, do something? Could we design something that spin move, but no charge is moving, and do something good for us? And that is the main theme of this new field your generation should know, okay? Called spintronics. That is the application side. For those more academic or oriented, okay, you may want to learn how to add two angular momentum formulae, quite abstract. There are things called Kapsch-Gordon coefficients. And then the other topic will be, I mentioned about the exchange interaction that leading to ferromagnetism. We will do a little bit of this in the helium atom discussion later. And final remark, we know how to do L plus into a half, and we know how to add half into a half. But in general, when we have 5 electrons, we have half plus half plus half plus half plus half, right? So there are many possibilities. Therefore, at least we know that we can add this 5 spin together to form a total spin that can be 1 or even 2 or 3/2. At least it's not half. And then we have 5 electrons. Each one has its own orbital angular momentum. We add it up into a total angular momentum. Okay, so a retro question is that, how about in general, what to do? You are given an L and you're given an S that is not half, what to do? So here's, I give you the rule again, but very natural, okay? All in all, you have many J's that could go from the longest Z component to the shortest Z component in step of 1. Now that is quantum angular momentum in quantum mechanics, basically, okay? So that is the general case. You will have more J value, but run through from the longest Z component to the shortest Z component. And after, underneath each J, there will be 2J plus 1 values. That's it. So what's next? The next topic we will discuss is how spin and orbital angular momentum interact inside an atom. We will find that there will be an interaction term that goes like S dot L, and that is called the spin-orbit interaction term. After we understand this term, then we can move on to understand what we discussed in the experimental data comparison. There is something called the fine structure. It means even the 2s2p state from Schrödinger equation without anything add to it, they are degenerate. 2s and the 3p's, they're all degenerate. However, data set, nothing externally applied to that, to the hydrogen atom. There's a S, there's a P, something split into 3 different values. How far we can go using perturbation theory to understand this n equals 2 situation. And that is called the fine structure. So we want to understand this. And in the first step, we want to apply spin-orbit interaction as a perturbation term. So the next thing that we will do is to explain a little bit about the physics of spin-orbit interaction. So let me motivate that part, and then we will do the detail after the break. I just mentioned that in a hydrogen atom, we will have an additional term that goes like S dot L. Let's get the big picture. Okay, that's important. Some of you don't worry about the details, the derivation, things like that, okay? But you ought to know the big picture. So here's the big picture. We have the electron. We have the nucleus. We have the electron, okay? Even in a Bohr model, very baby level way, the electron has orbital angular momentum, okay? Orbiting, all right? And for this motion, we could sit at the electron and think what is the motion, the relative motion of the nucleus. So the nucleus will be also orbiting around the electron, okay? But be very clear, this picture actually comes from the orbital motion of the electron. Only that we want to sit on the electron and then feel or sense that it is the nuclear motion around the electron, okay? The nucleus is a proton. So this motion amounts to a current loop, right? And therefore, there will be a magnetic field. Okay, something called the Biot-Savart law, you have learned. Therefore, in summary, it is the electron's motion that is generating a magnetic field acting on itself, because in this relative motion, there will be a magnetic field at the center of the current loop. That is where the electron sits. All right? So it is the most important concept for the big picture is the electron's own orbital motion generates a B field on the electrons itself. Okay? And now the second part is that the electron has a magnetic dipole moment due to spin. Okay? So the electron has a spin magnetic dipole moment, and now there's a field due to its own motion. The field goes like it's proportional to the orbital angular momentum, because that's the source of the field. And then you have a magnetic dipole moment that is proportional to the spin angular momentum. Okay, so we are up to this point. The orbital motion generates a field on the position of the electron, yet the electron also has a spin magnetic dipole moment. We look for an interaction energy. It must be minus mu dot B. Therefore, it must go like mu S dot B. It must go like S dot L. And you have this spin orbit interaction term. Okay, so that is the big picture. Only that with this picture, we do not know what appears as the prefactor. Okay, what is in front. Nonetheless, at the end, after even you do very serious derivation, it is S dot L. But we know what is in front, a very complicated factor. And that factor is also important to point out some physics. Nonetheless, it is easy to understand that there will be some additional term in the hydrogen atom Hamiltonian that you have ignored so far. One of them is S dot L term. This is called spin orbit interaction. Okay, so take this picture with you, and after the break, we will work on this picture and get this prefactor done. But unfortunately, we can only get this prefactor done up to a factor of 2. So there is a factor 2 or half that we will not explain it. And then I will quote the real result. Okay, we can work it out up to a factor half. Okay, so that will be the topic after the break.